Good afternoon. Welcome to Calculus in the PM. I'm your host, Mr. Shindelka. And as Ashton was wondering, I'd like to have a message from my sponsors. I'm my own sponsor. Surly Cowpuncher brand steel wool. Works on the most ordinary stains and mishaps. Nothing burns my beans more than inferior water steel wool. Surly Cowpuncher brand. Surly Cowpuncher brand is guaranteed not to wither under the most intense scrubbing conditions. Son Papa Joe. That's me. Okay. Surly Cowpuncher. If you need steel wool, talk to me. I can hit you up if you see it in most retail outlets. Kresge, Walmart, etc. It's good stuff. Volume is an integral. We know area, do we? I hope so. Area between two curves, top curve minus the bottom curve. We're going to extend that a little further now into three-dimensional things. Now, there are some basic volume formulas and ideas of volume you need to have down. I think you know for a prism. What's a prism? An example is a box is the simplest prism, right? Length times width times height. 3 dimensions, you got to multiply them, right? If you had a rectangular prism, you take the area of the face, a rectangular, I said a triangular prism, for example, though, before we even get into it. So if the front face, sometimes the base, the area of the base will be on its side. And I said this is like this, right? As long as I can find the area of this triangle, and then multiply it by the length that it extends back, I've got the volume, right? A cylinder, what's the area of a circle? Pi r squared times the height, or the length that extends back, right? We understand that. Because the whole idea here is, we're going to have to find the area of something, then we chop it up into little sections like this, and you could add up an infinite number of thin strips. Think of it as like slices of paper, right? And you add up all those tiny little slices, and you've got the full volume of this. Because it won't be just this simple then. What if it's a circular area, but then it extends, and it has some weird shape at the end, but it's all circular, but it's, different. That's where we extend this to. Well, we take the area of this front disc, the area of discs in the middle like this, and keep chopping it like pieces of paper, slices of bread. That's where we're going to extend this. And so basically, I just went through some of the details in here. Now, the whole idea is that if you have an irregular shape, doesn't matter, whatever though, it's the area of this slice here at the front, slices in the middle. You see how you've got this 3D slice here, right? If you add up all those little areas, you're going to get the little areas, and then the volumes of those tiny slices. You've got the net volume, the total volume. Okay? So that's what this is getting at, this idea. There's some good stuff in here. More about that after. We'll start. Volume of a solid. The definition of a solid of known integrable cross-section area. So if you can find the area of a face, and it's got a slight width from A to B, it's the integral from A to B. And there it is. So the volume function is, as long as you can find the area of something, this is those thin slices that I'm talking about, the dx, right? And you know how with the summation formulas and stuff like this, that just means that it's adding up an infinite number of extremely thin, close to zero slices, right? Approaching zero. And from whatever value A to B, 2 to 7, -5 to 3. Okay? Let's just try this out. Now, often it is, the toughest part of doing this is not the calculus, it's the setting up and visualizing some of these. Because sometimes you read something and it's like, what? Well, slow down. Sketch a solid, and its typical cross section. Is it a circle? Is it a square? Is it a rectangle? Is it a triangle? Usually it'll be some geometric shape. And I will assume you know pi r squared, and I will assume you know how to find the area of a triangle 1/2 base times height, etc. Find a formula for that area then. That's what I'm assuming you can do. Find the limits of the integration, like from 3 to 2, or 3 to 7, or something like that. Those are the limits. Those are the limits of integration, 1 to 2, okay? And then integrate. That part is usually, it's setting it up. That's the toughest part. Example here, square cross sections. Now imagine if I didn't have this drawing here. You have it there, but read this. A pyramid, 3 meters high. So once I hear pyramid, I think I got the shape. Has congruent triangular sides. Okay, so that means all the triangles are the same. Square base pyramid, 3 meters on each side. Each cross section of the pyramid parallel to the base is a square. So meaning if I chop this, now you notice that this pyramid is drawn on its side. Why is that? Just to make the math more familiar. Because now you're talking x-axis as you go this way, right? That's the only reason why. You could do this with the y-axis. Okay, and they state here, each cross-section of the pyramid is parallel. Oh, each cross-section of the pyramid parallel to the base is a square. Okay, that makes sense. Find the volume of the pyramid. This is something you probably could do, should. Do you guys know how to find the volume of a pyramid? Using... yeah. Now, the volume of a pyramid is 1/3. We'll pretend it's even possibly a rectangular base. The base is area, though. You know, length times width. In this case, it's a square. So the area of the base times the height. Now that's old school. That's grade 9, 10 kind of geometry, right? By the way, though it's good to know. So that's basically taking a box and then making it into a pyramid. The volume of a box is length times width, which is the area of one face, and then extending it for that height. I just want to say, how does this work with a cylinder? What's the volume of a cylinder? Do you guys remember? We just said it before. Pi r squared is the volume, or the area, times the h, height. I'm throwing this in because problem-solving skills. What about a cone? Do you see how a cone, I'm going to draw a cylinder here. A cone is basically, I should say, a cone is to a cylinder just as a pyramid is to a cube, right? So yeah, you got it. That's the cone inside here. It's, again, 1/3. I'm just throwing this as an aside because you might come up with some problem-solving skills that you might be able to take a shortcut sometimes. You don't have to use calculus if you could see a geometric shape that works with something, okay? Now, back to this problem at hand here. Sketch the solid. Okay, that's sketched. Typical cross-section. Find the formula for the area of that cross-section. A typical one. Sure, the one at the end here is a 3 by 3 square, but that's not useful to us because that's not every square. It's not constant, right? So what would the area of this be according to these measurements? Well, what are these measurements right here in the middle? They're giving us x's, right? So isn't this kind of like, if I took this and drew it face on, x by x. So the area is x squared. The area is a function. I'm going to say the area as a function of x is equal to x squared, okay? So come up with the area of one of those faces. And that way that x could be as large as 3, it could be as small as 0, right? When x is equal to, so if this was x equals 1 right here, that would mean it corresponds to 1 by 1 by 1 by 1. Okay? That's what that drawing's trying to represent. Then what? 3 and 4. Find the limits of integration. Where are you going from to what? 0 to 3. Because at 3, we've stopped, right? Okay, so that's the limit, 0 to 3. We'll do 3 and 4 together and integrate to find the volume. So the volume function, I'm going to write volume as a function of x. Whenever you have that little bracket variable, that means as a function of, right? And do you notice how, like here, this is volume as a function of area and height, right? We don't put AH there, though. I'm trying to get volume just strictly as a function of x. And according to what we were just told, as long as you have the area, well, first of all, the limits of integration. 0 to 3, we said that. Then, the area of one face, x squared. Now, I'm going to pretend that I have this width right here. So I'm taking a slice with actual width. What's that width called? dx. That's that little width that we're trying to minimize down to 0, right? That's what this dx represents here. Okay. So that's how you get volume out of this, right? Now we do the integration. That part's easy, I hope. Tell me what the antiderivative is.
1/3 x cubed.
Now, you could choose not to put a front bracket on this because this is one thing. If it makes you feel better, though, I'll do this. I used to not do it most of the time. Okay, so now it's just arithmetic, right? And we just toss this in here. 1/3 x cubed 27, right? 1/3 of x 27 cubed. So 9, right? I think you said 9. Minus 0, so 9. Was I given units in this case? Meters? Yes, I was. So this will be meters cubed. We know a few things about volume, and one of it is units cubed. If they don't give units, don't have to put unit cubed. Okay. And if you wanted to, you could verify that's the case with the old school formulas. 9 meters cubed. Now, that's fine and easy when I'm doing it. Dane, I forgot to give you this. You want to just grab this? It's from the other day. It's what I had on the board earlier. Let's try it with something that's a little different. Circular cross sections. So you know it's going to be a cross section of a circle, but how does it vary? Okay. It's assumed knowledge. Pi r squared is the... Okay, so when you have circular cross sections, adapt the area formula for a circle to the given situation. Let's use this, and we'll try it with our calculator too. The region between the graph of f of x equals 2, here's the function. That's what you'll enter in the calculator eventually. 2 plus x cos x, don't start with the calculator yet. And the x-axis over the interval is, so here's the graph, right? And it's rotated, revolved around the x-axis to generate the solid. So you can imagine taking this and just twirling it around the x-axis. You see how it's like a potter's wheel kind of thing, right? Or a lathe. You get that shape. Everybody's cool with what this represents? So when you see the phrase revolved around the x-axis or revolved around the y-axis, figure out what the shape is, and then just, some people aren't good at imagining it, and you can actually do this without imagining. But it's, try to imagine the volume. If you're good at it, it helps. Okay. And then you say, well, if I revolve that around the x-axis, it's going to be a circular shape. So here's a typical cross-section right there, right? Drawn on its side. So the first thing I recommend you do is say the area of the face. In this case, well, we know area in general is pi r squared, right? How are we going to find this radius here at a given x value. How high up is that? What would you put it into to find? It is the y value, so what are you going to do? Yeah, that's the 2 plus x cos x thing, right? That's the radius. Now, do you guys get that? So that works even if the x value is from here, right? That's the radius. Anywhere. That's the radius. Any of those circular cross sections. So we got to take a variation of pi r squared. So we're going to say pi, and instead of r squared, we're going to replace it with the function squared. Y'all agreed with that? Okay. Now, if this is an AP exam, I could have just, because you're looking for shortcuts, but we're learning right now. I would probably have just put f squared there, pi f of x squared. I'd put a bracket around the whole thing, though, just to make sure it's really clear, okay? The function squared. Now, if I know what the area is, and I do, I'm going to put it into a volume function. My volume function will be, well, it says, pretty clear, -2 to +2. That's my limits. That's from here to here, right? -2 to +2. Okay, good. And then I put in my pi r squared stuff. That's the area function. Now, because you're learning to take shortcuts on an AP exam, I'm just going to call this a of x. You can write this out fully, and you'll actually enter in your calculator, pi 2 plus. So. Okay, because that represents what we just wrote above, and then the thin little disk width, dx. Put it into your calculator. Let's see what you get. Okay, so when I entered mine in, I get 52 point, we're going to keep at least 3 decimal places, 0.429. What's that?
Because we both got 25.13.
Ah,
This is square.
you're missing the square. My square is off the map here, but here, if you take a look. You see how I have my square though after, did you square your x or did you square the whole expression?
It squared the x. It squared the x.
That's a,
And one
okay,
bracket.
guys, you're wasting time. Okay,
No, Ryan also squared the x.
yep. It's the entry, double bracket there. Be careful with your brackets,
I put it right before the bracket.
because when you enter this in the calculator forces you to use this bracket, right? I just put it in blue there.
Yeah.
And that's where an error could come up. So make sure you're getting 52. And 4288 if you wish. I'm not going to mark you wrong for going 4 decimal places. It might be safer to always do that. Yeah?
So in a question like this, would you want units cubed?
No. If it doesn't give you centimeters, meters, etc., just the number is fine. That's implied though, and that's good thinking. There's nothing wrong with doing that. I'm just not going to require it. I will require it if there is an actual unit.
We don't have these absolute values.
No, don't use absolute values. It's squared, right? So you're good with that. And there might be a situation, just don't. Okay? Now, what about washers, donuts? Because what if you have a hollowed out section? The region of the first quadrant enclosed by the y-axis in the graph of y equals cos of x and y equals sine of x is revolved around the x-axis to form a solid. Okay. I need a quick sketch to, and we're going to assume without a calculator. So I know where the y-axis is. I know how cos of x starts. I know how sine of x starts. Okay. That region is revolved around the x-axis to form a solid. Now, do you guys see what that'll be like? It'll be like a bowl, kind of, right? You can imagine this twirled around, and I'm talking about this area here, right? That's what this is described. Now, you need to know that because you need to know what's the top function, what's the bottom function. The way I drew it, hopefully it's right, my red is y equals cosine x. My blue is y equals sine x. Top function. Now, from the previous section, if I wanted this area, top function minus bottom function in an integral, right? Dx. Where do they intersect? I hope you know where sine and cosine are the exact same. The exact same being the y value is root 2 over 2. Pi quarters. 45 degrees in grade 11 parlance, eh? Okay. If you're not familiar with that and you're like having a brain fart or whatever here, doesn't this, you know how this goes on? This is 1 pi, this is half a pi. Okay, yeah, they intersect at pi quarters. You could maybe reason that out too without knowing your triangles and in an emergency. Okay, so we're going from 0 to pi quarters. Now, yeah, that does involve a few concepts. You're taking together concepts you've learned over the last 12 years, tossing them in together. Hope the ones from grade 6 and under are really in there. Now, think of this. When you take a slice and you twirl this around, now, I'm not going to make my drawing so messy that you see that your underside will also be like this, and I'm not drawing with color here, it's going to, right? This is the cross, like this is what the 3D object would look like. It's kind of like a bowl, right? Can you imagine that? Now, if I took a slice of that, it'll look like a donut or a washer. This is the washer method. And if I'm talking about a washer like from nuts and bolts, a washer, if I was looking straight on from this side and I chopped it, I would have a washer, and I'm going to use the outside ring as the red, inside ring as the blue, and I'm taking red and blue from outside, inside, right? That's what I'm talking about, this washer. And each one will have a cross-sectional area. Now, two different radii. Big radius minus small radius, right? Now my red and blue correspond to cosine and sine, right? There's a reason. Does it make sense that my area here, the shaded area, if I'm strictly looking at this area, if I told you, and I'm just going to make up a number, the big circle has an area of 25, the little circle has an area of 10. What's the area of the washer? It's the difference, right? Big area minus the little area. 50. Now I just made up numbers, the area. So what we really want is an area function that is, I'll get this down lower here. Well, how would we set it up? I was going to just write it down. What's the area of the big function? Radius pi r squared in this case. Pi, but what's my yeah. So big area minus little area, right? So we got the cos x. Got the sine of x. Now that's the first thing, is to come up with the area of the washer. Then the rest is putting it in the integral. from 0 to pi quarters. Those are your limits of integration. Volume as a function of x is equal to. Now, you could be more compact and isolate some things, but I'm going to just write it out so that it works the same every time. It is 0 to pi quarters of, big bracket, the area pi cos squared x minus pi sine squared x dx. That's no different than the others, in a sense, as long as you remember big minus little. How do you solve that is what you're saying. Now, I could use a double angle identity. I'm going to get you to now use, once you have this set up, do your calculator. Or, no, I'll give this to you. You guys know the double angle identity you can apply here? Yep, cos squared minus sine squared. This is what you're... Don't fret about memorizing all these. Cos squared minus sine squared. Cos squared of theta in this case. I have not seen evidence that you had to memorize double angle identities, but maybe if something like that, they sometimes give you formulas. The volume of a cone is 1/3, stuff like that. Sometimes you might have something like this, where it might be useful in this problem. How could you apply that? Well, you see that pi is a common factor, right? You could have yanked this out and put it out in front of the integral, right? Cancel these. And then you got cos squared minus sine squared of x, right? Isn't that the same as cos of 2x? Let me double check here. Yep, I did remember that. Okay. So I'm going to do this. I was going to get you to do it on the calculator. This can be done. So pi cos of 2x dx. Once you have this, I can do this integral. Can't I? And well, I know it's got pi in front. I'm going to leave that outside. The antiderivative of the cos 2x. Cos would have come from sine, right? I'm going to leave a space in front because I know there's a number. But if I did the derivative of sine of 2x, I don't get cos of 2x, right? Because then you do the derivative of the inside and you got a 2 hanging out. So we need the half. Now, if you don't like that, use u substitution for u equals 2x, and then it'll bring the half out. Now it's just evaluation. Do you remember? Well, when you put pi of, I'll write it out.
Sine of 1/2, say 1/2, pi over 2.
Sine of 2 out of 4, so sine of pi half. That you should be able, minus the half sine of 0 times 2x. So 0 still. Sine of 0 is 0. Agreed? Starts at 0. Half was, what was it?
Sine of 1/2, or pi over 2.
Or pi halves, yeah. That's pi halves right there. 1. Okay. So 1/2 minus 0. You guys see this? Pi halves. Okay. Now, we'll stop this moment here.